In this lesson, we will construct an updated energy level diagram for hydrogen using quantum numbers. Let's create an energy level diagram for hydrogen consisting of all its states that have n less than 4. To construct our diagram, we must start with determining what all our states are. So let's begin with the very first possible state, when n equals 1. If n, our principal quantum number, is equal to 1, then L, our angular quantum number, has only one possible value, 0. This is because L can have values from 0 up to n minus 1. Since n minus 1 in this case is equal to 0, we only have one possible value. Now our third quantum number, m, can only go up to the absolute value of L. So thus, m can also only be equal to 0. Overall, we have one state with n equaling 1. This state is described by the numbers 1, 0, 0. On to our states with n equaling 2. This time, L can have two possible values, 0 or 1. When L is equal to 0, m can also only be equal to 0, as we determined earlier. When L is equal to 1, however, m can have a value of 0, positive 1, or negative 1. This is because m goes up to the absolute value of L, but has both positive and negative values. This gives us 4 stable states with n equaling 2. These states are 2, 0, 0, 2, 1, 0, 2, 1, positive 1, and 2, 1, negative 1. Lastly, we have our states with n equaling 3. When n is equal to 3, we can have possible L values of 0, 1, and 2. As we've determined before, when L is 0, m also equals 0, and when L equals 1, m can be 0, positive 1, or negative 1. Similarly, we can now determine that when L is equal to 2, m can have possible values of 0, positive 1, negative 1, positive 2, and negative 2. Altogether, this gives us 9 possible states with n equal to 3. These states are 3, 0, 0, 3, 1, 0, 3, 1, positive 1, 3, 1, negative 1, 3, 2, 0, 3, 2, positive 1, 3, 2, negative 1, 3, 2, positive 2, and 3, 2, negative 2. Time to put it all together. Beginning with our lowest energy level, when n equals 1, we have one energy state, where L is equal to 0 and m is also equal to 0. Moving on to n equals 2, we once again have a state where both L and m are equal to 0. This time, we also have 3 states where L is equal to 1. In these 3 states, m has values of negative 1, 0, and positive 1. Lastly, we have our energy level when n is equal to 3. We again have one state where L is equal to 0 and 3 states where L is equal to 1. Our last set of states is when L is equal to 2. Here we have 5 values for m, which are negative 2, negative 1, 0, positive 1, and positive 2. This is hydrogen's complete energy level diagram for all states with n less than 4. There's a few differences to note between this diagram and the diagram created by Bohr's model. Though Bohr had the spacing between energy levels correct, his diagram contained only one energy level for each value of n. As we can see in our diagram here, each n actually has multiple energy levels. It's also important to note that this diagram is for hydrogen, which only has one electron. This makes it a special case because for a specific value of n, all states have exactly the same energy, which is why we've drawn them in line with each other. This will not be the case for multi-electron atoms.